The other aspect of the elasticity is Hooke's law. We want to define or state what the law says. Hooke's law simply says the force that is applied to an elastic material is directly proportional to the extension. That means, what do we mean by that? If you apply very small force, you get very small extension. If you apply very large force on this, the extension also increases. That means the higher the force, the higher the extension. The lower the force, the lower the extension. That tells you that the force is directly proportional to the extension, provided the elastic limit is not exceeded. You should not go beyond the elastic limit. You already know that the elastic limit is the highest point reached that the object has the tendency to return to the original point. So, for Hooke's law to be maintained, the force must be proportional to the extension, but the elastic limit must not be exceeded. Now, mathematically, you can write the force is directly proportional to the extension. The force is proportional to the extension. You can represent force as F. F proportional to E. You can take extension as E. Now, this one becomes a variation. And in variation, we always change the proportionality sign. Changing the proportionality sign to an equal to sign will now become F equals, instead of this one, it becomes a constant K, Ke. Now, in the analysis of variation, we always find the constant. The constant here is K. So for me to get K, I divide both sides by E. I will now have F over E equals Ke divided by E. I have divided both sides by E. So E becomes F divided by E. So the formula for K is F divided by E. And K here is known as force constant. The constant here is known as force constant. Force constant. Now, how do you define force constant? If you want to define force constant, you look at the relationship. It is force divided by extension. And F divided by E in mathematics is the ratio of the force to the extension. So if you want to define force constant, you say force constant is the ratio of the force to the extension. Therefore, force constant is just the force divided by the extension. The SI unit for force constant is, the force is in Newton, the SI unit for force is in Newton, divided by the extension is in meter. So the SI unit for force constant is Newton per meter, or you write it this way, law of indices, the same as Newton per meter. That is how you can get the analysis. So therefore, the force constant is F divided by E, force divided by extension. That is for one state. For one state, we can get, we say for one state, K equals F divided by E, the ratio of the force to the extension. This is for one state. For one state. Now, if you have more than that, let us say you apply a small force. That is force number one. There must be an extension. If I apply a small force on this, I say F, the force I apply, and the small extension. Then I increase it. That means I have got another force, another extension again. So if that is the case, if that is the relationship we want to use, the moment you apply force number one, the extension is E1. Have in mind we are saying F divided by E. So if it is force 1, it is force 1 divided by extension 1. That must be equal to the force number 2 divided by the second extension. That is what we are bringing here. So when you have two different states, the first force you apply divided by the extension applied at that point equals the second force divided by the second extension. That is what Hooke's law states, that the force is directly proportional to the extension provided the elastic limit is not exceeded. So if that is the case, we move to another state, another form. Mathematically, there must be something you should know, and that is K-reading conversion. This one confuses people a lot. Some people will not understand the scale reading, how to convert scale reading to extension, or how can you use extension to find the scale reading. So you have to take a look at the analysis we are doing for proper understanding. So let us say we have scale reading here, scale readings, and let us say we have extension here. If you are able to understand this one, your problem is solved. The scale reading is also in millimeter because it's a measurement. Extension is also in millimeter this way. So if that is the case, let us look at highlight here. At the beginning of the experiment, like this one, I have not applied any force on this. Therefore, there will be no extension. You can see it. The moment there is no force, no extension. So at the beginning, the force is equal to 0. When the force is equal to 0, there will be no extension here. So there is no value here, no value here at the beginning. Now we move to another state. Let us say the first extension here, we can call them any values of our choice. Let us say this is x1. Values under the scale reading x1. We can call this scale reading x2, scale reading 3, scale reading 4. And if I want to waste time, I will even go to scale reading 5. Now I want to get the extension E1. Have in mind against x1 will be E1 extension. X2 becomes E2 against that. Here this is E3. This becomes E4 and this becomes E5. If that is the case, we move further. How to get the relationship that will exist here. In simple term, when I want to do any analysis here, I will just say, if I want to use the first two figures here, I will use x2 and x1. That is x2 minus x1. When I take this minus this, whatever answer I get will be the same as the second extension minus the first extension. E2 minus E1. Let us say you are now interested in E2. You want to find E2. If you want to get E2, you take E1 over. So you have x2 minus x1 minus crosses become positive. E1, that is equal to E2. When you want to get E2, what you do is subtract this and this. Subtract this figure. The figure that is against E2 that you are interested in is this. This minus this plus this will give you this answer here. Anytime you want to get E2, you say x2 minus x1. Whatever answer you get plus E1 will give you this. Let us say you want to get E3. The figure that is against E3 is x3. So it becomes x3 minus x2 plus E2. So if I want to get E3, it is x3 here minus x2 plus the E2 at the top. If you want to get E4, the scale reading against E4 is x4. That becomes x4 minus the value on top that, which is x3, plus the value above the extension required, that is E3. So in simple terms, if you are confused, what you do, you take 1, 2 at a time. If you take this and this, just say x5 minus x4 correspond to E5 minus E4. E5 minus E4. Even if it takes you a day to understand that, make sure you do. Now we move to the analysis. All of these analyses are on Hooke's law. It takes us now to another phase, and that phase is graphical representation of Hooke's law. How can you represent this thing graphically? We said the force is directly proportional to the extension, provided the elastic limit is not exceeded. So anytime you apply the force, you increase the force, the extension will increase. When you reduce the force, the extension reduces. So in mathematics, anytime two quantities will increase at the same time, or two of them decrease at the same time, the graph will always be from the origin. We are dealing with two quantities. We have the force here in Newton. We have the extension here in meters. So anytime two quantities are directly proportional, that means increase in one of the quantities will lead to increase in the corresponding quantity. There must be a straight line from the origin here. You have a straight line moving from the origin. So if that is the case, we now proceed. That because tells you that you have to find the gradient. Anytime you have a straight line, you find the gradient. And for you to find the gradient on a straight line, you locate 2 points on that line. If I locate 2 points on this line, any 2 points, I can take this point and this point, and now join them with a right angle triangle. If I join these 2 points with a right angle triangle, I will have an analysis this way. That is the right angle triangle, and in which the 90 degrees is at that point. That makes it 90 degrees. Now there is a vertical line here. There is also a vertical line here. Vertical lines are parallel. These parallel lines they are equal. Any vertical line I see is represented by F. So here becomes F. This one also is represented by E horizontal line. I will put E here to represent that analysis. If that is the case, we proceed. We now have the slope. We can get the slope. Formula for the slope is always increase in y divided by increase in x. Now in this case, the y value here is f divided by the e value here is, the x value here is e. That means the y value here is f, the e value, x value is e. You have f over e. But a few minutes ago we said f divided by e is the same as force constant. So anytime you plot a graph of force against extension, the slope of that graph is known as force constant. That is how you get the force constant. So the force constant of force against extension graph is always by plotting a graph of force against extension, and the slope is always known as force constant. Now there must be energy. Have in mind, when you are stretching a material like this, you exert energy, you experience energy. That means we are using energy to extend this one. So if we are using energy, what will be the analysis that we put, or what will be the equation that we put to get the energy? Now we have the right to say that the energy stored in this material that I am stretching here, the energy stored is the same as the work done or area under this particular graph. That means we can get energy stored equals area under force against extension graph, force against extension graph. So anytime you want to get the energy stored, you use the area under force against extension. Already we have a graph here of force against extension. So this particular one I am shading. The moment you are able to find the area of the shaded region, that is the energy stored. Now let us get equation for that. The energy stored now become, this one I have shaded is a triangle. And if you recall in whatever level in the mathematics, the formula for area of a triangle is half times the base times the height. So the energy stored is given by half times the base here from here to here is E, and the H is the height from here to here. That becomes F. So that equation is giving us the energy stored as half E times F is the same as F times E. I want to put the capital letter first. So the energy stored in any material that is stretched, the energy stored in that material will be half multiplied by the force times the extension, which is the same as 1 times Fe as Fe divided by 2. So Fe divided by 2 is the formula for the energy stored in any material that will stretch. You can go further if your mathematical background is very strong. We know. Few minutes ago in Hooke's law we said F equals Ke. If F is equal to Ke, wherever I see F I will put Ke. Have in mind I have an equation that says half of Fe from here. But I already know that F now is Ke. So wherever I see F, I will put Ke. I'm having half of F is here, I put Ke. That means for this F, the result here is Ke. We have another E here. So the energy stored is also half. K is here. E times E becomes E square.